Yeah. Yeah.
Yeah.
Let's get it. Exists or D&E as limit approaches infinity. There are so many rules to understanding calculus. You see, if a function has limits approaching from left and right at x equals c, and the y values match, then the limit exists. These rhymes can't resist, but if the limit fails to exist, think of reason 1, 2, 4 down the corridor to understand what it means to not exist. Yeah. 1. The one-sided limits aren't equal, and then there's 2. The function don't approach no finite value. 3. The function just keeps oscillating all around you. 4. The x value approaches an endpoint of a closed interval. So think of right and left-hand limits and see if it fits. You'll understand limits better, never play a quiz. Want to understand D&E more graphically? When one-sided limits exist, desist, but they are not equal. My rhymes can be so lethal. The function jumps at the point, brother path subjoined. Or the graph has a vertical asymptote at x equals c, and it blows up to plus or minus infinity. Yeah. Or there's behavior that's oscillatory. This sort of stuff has a tendency to make me worry. Don't forget me, continuity function continuous at x equals c. Only if it's defined, and limit as x approaches c exists. And the limit equals f c. Get off my continuity. Yeah.
Differentiation is easy to picture graphically if you consider what it means to differentiate. Just know that a function's derivative is really nothing more than a graph of the slope of the function at every point. To picture it more visually, just think of a single point on a function. The derivative at that point is the tangent line. Nice V-line. Man, this is so easy. Ha ha ha. Now, consider the math behind the tangent line. It's the rate of change. I know it's strange, but it's just the change in y over change in x. Boy, I could go for some checks. Haha. Alright, to analyze derivatives, I ask that you think of the limit as h approaches 0 of f of the quantity x plus h. The quantity minus f of x, all divided by h. I decided not to rhyme.
Rebel.
This limit definition's all the analyzing you need, and so thank you for your time, but let's move on to application. So I didn't just talk about derivatives because they're cool. Funny enough, they have some very important applications, like finding a rate of change at a specific point, or even finding critical point, or minimum and maximum values. Oh, hello stranger, how do you do? Or finding absolute extrema. Boy, you're being extra. Or finding the shape of a graph, or solving optimization problems. Boy, Michael and Cabo's awesome. And so much more to do with derivatives. They're so useful, I see why I'm taking this class. Oh, don't be crass. Yeah, like, come on. Calculus is useful. Like, I swear. Yeah.
We just finished derivatives. So let's take it back now, y'all.
Ooh, he gonna take it back. Woo! Yeah. Woo!
Take the derivative methods and flip it all around. We about to go to get our integrals down. Basically the opposite, ain't nothing to it. Take the final equations and reverse this. Oot. Yeah. Integration and antiderivatives, it's all the same. Make an equation derived to the original. Use your brain. Take your equation and add an integral symbol. Then throw a d with the variable you're using over on the right. Tight. If you're integrating a constant, multiply your variable. Ain't nothing to it. Just remember plus c. Make it viable. After unbounded integrals, you always add a plus c. Don't, and Velasco will kill you.
Yes, you will.
When you integrate a variable, add 1 to the exponent. Take that new value to apply as the dividend. Don't forget that plus c. Now you got an equation to represent the integral derived for the original. This is what we call an indefinite integral, a simple equation which says it all. You can solve for the integral value at a point, and solve for plus c with a value. Doink. Now let's step it up to definite integrals.
Yeah.
This gives you the integral along an interval. Simply add a number on top of the symbol, then a number on bottom. Simple. Take the integral as you would normally. This time you don't need a plus c really. Plug in for the top value a, subtract by the bottom value b. This gives you the value for the definite integral bounded from points a to b. Yup. A, bounded integral is the change in the original. The integral of f of x from a to b is equal to delta f of x from points a to b as well. Yeah. First fundamental law of calculus. Duh.
Oh, yeah.
A, indefinite integrals gives the equation. Yeah. Get the value with a point. Yeah. Definite gives back a value. Yeah. Get the change in the original. Yeah. Now, without direct values, there's many ways to approximate using different methods you can still integrate, such as a Wright-Riemann sum. To use it, you just don't be dumb. Get a table of values representing the graph you'd like to integrate, starting from the right side, cause it's in the name, mate. Take the value of y or f of x, then multiply by the change of x until the next two apply. Yeah. Then sum this for all the values given to you. End up too far left. Sum it for the approximation that you set out to get. Yeah. A.
Yeah.
A bounded integral represents the area between a graph and the x-axis. Take the derivative of it and you'll find exactly where the graph is. If you take the integral at a point, it gives you the distance it is from the axis. Yup. An integral can undo a derivative, making it useful to find the graph of x from the first derivative. Integral gives you the total area from a to b, so if a graph represents the rate of production c, you can find the total amount made on the bounds, dummy. Yup. A. Integrals. Yeah. Antiderivatives. Yeah. Undo derivatives. Yeah. Finding the area. Yeah. Finding anything. Yeah. Now it ain't that hard. Yeah. Now let's take it over to something a little more interesting. Yeah. Yeah.
He said it.
A. Yeah.
Now drawing slow field, it's about to get real. We've got to substitute ordered pairs into the derivative to compute slope values.
Yup.
At this point, gotta go. Good doinks. Let's construct short line segments. It makes a lot of sense on the dots to approximate the slope values. And for a particular solution, sketch in the curve using the initial condition. It's your mission, and guided by the tangent line. It's sublime. Oh yeah. Let's get on a train, move on. Next mathematical station to find general and particular solutions of differential equations. First, you gotta separate the variables. Gotta mix all your marbles. Then you gotta integrate both sides, putting C on the side with the dependent variable on the bottom of the differential equation. Now that was just general. Let's move on to particular. You must listen, follow these steps. Of course, there is an initial condition. Get to a point where it is easy to substitute in the initial condition, solve for C. Then use the C you found, you see, and continue to find for f of x, if need be. Yeah. Another thing about differential equations you must keep in your head is this great thing called Euler's method. Listen to this step by step. Keep in mind what I said. Start at the given point on the graph. Look at me solving great math. Calculate slope at this point. By using differential equation, don't disappoint. For a given value, delta x, calculate the value of delta y. Let's see how this affects the math that we'll have to buy, and use the equation delta y equals dy dx delta x. Yeah. Yeah. Add delta x to x and delta y to y. You might ask, why? Just why? Very soon, you'll see the point. By that I mean, you get a new point. One last step, don't you tire. Just repeat the process until you reach the x value you desire. Yeah. Now there's the growth and decay. I got a bunch of stuff to say. If y is differentiable function of t, such that dp dt equals kp l minus p, then p equals l divided by 1 plus c raised to the negative LKT, and limit of P of T as T approaches infinity equals L, the carrying capacity. So dp dt is at its max, which means the rate of growth of decay is increasing or decreasing the fastest. Where the function reaches half its carrying capacity, it can be written as L over 2, Math City.
Woo!
And did I also get to mention that this is P of T's point of inflection?
Yup, yup, ho, ho.
Sequences of series will bring the weaker to theories, so just don't know for series there are tests to see if they will converge or diverge from a finite value. I'd really like a cashier use the best test for convergence or divergence.
Yeah.
Nth term, if the limit as n approaches infinity doesn't equal 0, it diverges. For realsies, geometric series will really blow your socks off. Absolute value of the common ratio r less than 1 converges, more than or equal to 1 diverges, and to find the sum, know that s equals a over 1 minus r. Know this, and you'll be a star. P-series, where series form is 1 over n to the p. If p is more than 1, the series converges. But if p is less than or equal to 1, it diverges. And then there's alternating series, where there are a few conditions to show a series converges, so don't fight all your urges to test if the series alternating between positive and negative values. There aren't a lot of words that rhyme with values. Next, the series must be decreasing. And finally, limit as n approaches infinity of the absolute value of a sub n must equal 0. Integral, where f is continuous, positive, and decreasing. Look at the integral from 1 to infinity of f of x.
Yeah. Yeah.
Whether the integral converges or diverges, just know that the original does the same. If you forget these rules, you are lame. Root, look at the limit as n approaches infinity of the nth root of the absolute value of a sub n. If it's less than 1, it converges. More than 1, it diverges. Let's go. A ratio, look at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Say it once, again. Even write it with a pen. If it's less than 1, converges. More than 1, it diverges. Direct comparison if a sub n is less than or equal to b sub n and series b sub n converges, so does the original. And if a sub n is more than or equal to b sub n and series b sub n diverges, well, the original does that too. Limit comparison if the limit as n approaches infinity of a sub n over b sub n is greater than 0, then a sub n behaves the same way as b sub n. Taylor and Maclaurin can be so very boring, but if you remember the rules, you won't look like a fool. Provided the power series representation for the function f of x, a about x equals a exists, the Taylor series is f of x equals the sum from n equals 0 to infinity of f to the n of a times n, quantity x minus a to the n over n factorial in memorial. If a equals 0, you're no hero. It's just called Maclaurin instead of Taylor. I need a hit of my inhaler. Moving on, let's find the radius converges. Come on, and use the geometric series or ratio test, cause they're always the best.
Oh.
Come on, and set up and solve an absolute value inequality. You'll find your radius convergence. It all just makes much sense. Now to estimate the error of a series. Oh, much better. Use Lagrange error bound. It's mathematically sound. Now to discuss how to find the error bound. Find the absolute value of f of x minus p of x or r to the n of x is less than or equal to f to the n plus 1 of z times x minus c. The quantity to the n plus 1 all over n plus 1 factorial, where f to the n plus 1 of z is the max value of the derivative on the specified interval. Unbelievable.
Unbelievable. Yeah. Yeah.
Yeah.
Yeah.
Basic math 2.
Yeah. Yeah.
Yeah.
Yeah.
Woo-hoo.
Hey.
Ho ho.
Polar coordinates, they ain't no fun, but hey, we still gotta get them done. Not all that crazy, it's pre-calculus basically. Now we gonna apply some new concepts on it, baby.
Woohoo, baby.
Yo,
Yeah, yeah.
you wanna find the area of a graph. You already know, integrals where it's at. Basic formula, don't you forget it. For the polar area of a graph, you gotta have it. The integral of a graph's equation squared. All times 1/2 on the outside over there.
Yeah, yeah.
Bounded by radians for theta to have a set area. Yeah, it ain't really that scary. Yeah.
Ho ho.
Yeah. Now
Scary.
let's not forget our basic formulas. X equals R cosine theta. Yeah. Y equals R sine theta. Yeah. Converting it to rectangular form. Yeah. Battle through this like Operation Desert Storm. Yeah.
Desert Storm.
If you take dy dt divide by dx dt, you can find the rate of change for a theta in the range. 2. Find the rate at which the distance between two curves changes with respect to theta. Find w of theta, the difference between the inner and outer curves. Then find the derivative to w d theta. Plug it in. Yeah. If it's negative, yeah, it's decreasing, yeah. If it's positive, yeah, it's increasing, yeah. That's all you need to know for polar. So we about to end the rap because it's all over, yeah. Yeah.
All
Yeah.
over.
Yeah. Yeah. Shout out to my main man, Big V.
Woo, yeah.
Yeah. Yeah.
Big
Amonland
V.
is trash.
Trash.
Yeah.
Kerm forever.
Yeah.
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 Yeah. Yeah.
Yeah.